Let's talk about trapezoids. Specifically, we're going to talk about finding the area of a trapezoid. Now we see our formula over here stating that area is equal to 1/2 the height times your two bases added together, or times the sum of your bases. Now, one thing I want to notice, or one thing I would like you to notice, is that your height isn't necessarily an up and down. It's whatever is perpendicular to your bases. Notice that in this case, that distance isn't necessarily one of your sides. It's just whatever that perpendicular distance is between your bases, that's your height. Height doesn't necessarily mean up and down when it comes to trapezoids. It's just that distance in between the bases. So it's somewhat counterintuitive, but if you just remember, find your parallel sides. So given any parallel sides and any way that they're connected, say they're connected this way, neither of these lines would be your height. Your height is that perpendicular distance in between them. Let's work some examples. So this says a trapezoid has a height. Okay, I'm just going to draw a dummy trapezoid. There's a trapezoid. It says it's a height of 8.85 yards. So I know that's my up and down distance, 8.85 yards. And it says the bases measure 30.32, and 16.35. The slanted side of the trapezoid, ooh, it says slanted side, so that's one of my diagonals that isn't super important, measures 13.8. 13.18, I apologize, yards. Calculate the area of the described trapezoid to the nearest hundredth. Okay, so while we do have this slant height here, we don't care about it because what we care about is the actual height. So we just wrote down the formula. Area is equal to 1/2 your height times your base 1 plus your base 2. Let's fill in this formula. So in this case, area is equal to 1/2. Our height is 8.85. Our two bases are 30.32 plus 16.35. Let's go ahead and plug that into our handy dandy calculator and then find our answer. So my calculator is giving me an area of 206.51475, and that would be in yards squared. However, this says round to the nearest hundredth, so that means I need to round to this second digit after the decimal place. And will that 4 make my 1 round up or stay the same? It'll make it stay the same. So 206.51 yards squared will be my answer. Ooh, let's look at this one now. What is the total area of the trapezoid? It gives me my bases here and here, and it gives me my height. I don't even have to worry about whether that's my slant height or not, because I know right here I see this right angle that really helps me know that that is just my standard height. So I can use that same formula. Area is equal to 1/2 the height times B1 plus B2. So this case, area is going to be equal to 1/2 my height, which in this case is 5 4/5, plus, multiplied by the sum of 4 1/3 plus 14 and 3/5. And then again, I'll plug that into my calculator. Now, one of you guys might have a question on, does it matter which one's base 1 and which one's base 2? No, it doesn't. As long as you're plugging it in, think about it, it's addition. 2 plus 3 is equal to 3 plus 2. So that won't make any difference if you mix up the order. The only thing that really is important for you to keep straight is the bases are the ones that are being added to each other, and the height is the one that's all by itself. Okay, after plugging it into my calculator, I'm getting 54.90666, and the 6 begins to repeat. I'm going to assume, just like the last one, that I would round that off to the nearest hundredth. So for this one, that 6 will make the 0 round up. So I'll have 54.91, and this is given in miles. So this must be a huge trapezoid squared. Now let's find the total area of this trapezoid. Now, if we're looking at this trapezoid, a big decision that we have to make for ourselves is which one of these to use as the height. Well, this one has the right angles attached to it, so we know we're using this one. Area equals 1/2 height times base 1 plus base 2. So our area is equal to 1/2 our height, which is 2.45, base 1, which will be 1.93, plus base 2, which is 3.05. We'll plug that into our calculator, and we will get a area of 6.1005. And I guess I have been rounding off to the nearest hundredth, but this one actually does terminate there. It's not one of my continuing decimals, so I'm just going to leave it as that meters squared. Let's move on. Okay, same situation here, except we notice that our trapezoid has been rotated. Does that mean that this 10 or this 15.64 are those heights? No, those are still your bases. Those are still your bases, because your bases are determined by whatever lines are parallel. And obviously, this top and bottom line are not parallel, but it appears these two are. And we could prove that they are by these two right angles, which means, because we have the right angles here, this is our height, and this is useless information. So area is equal to 1/2 height times base 1 plus base 2. So our area is equal to 1/2. Our height in this case is 2.93. Our two bases are 10.93 plus 15.64. Again, we'll just plug that into our calculator, and we'll get our area. And that's going to give us 38.925. That was odd. Did that just go to the previous slide? It did. I apologize. 38.92505 inches squared. Now let's talk a little bit more about trapezoids. Now, like we said before, the top and bottom lines, or your two bases, to speak more accurately, because sometimes they're side to side like we saw in the last problem, have parallel sides, which means that we are always dealing with consecutive interior angles. Um, Now, concept you might remember from consecutive interior angles. It doesn't want to write over there. That's odd. They always add up to 180. So we're going to use this to solve a few problems. Let's look at this. I want to solve for angle 1. Now, I know angle 1 and angle 9 together make consecutive interior angles. So angle 1 plus 95 degrees equals 180. Make sure that you put that little angle symbol there so you don't think 1 plus 95 equals 180, because 1 plus 95 is 96, which is not equal to 180. Let's subtract 95 from each side, and we will get angle 1 is equal to 85. Excellent. Now we're going to use that same concept in order to solve these two, except we have angle 2 plus 55 in this case, equaling 180. So minus the 55 from each side. Angle 2 is equal to 125. Simple enough. Let's make it a little bit more complicated. Look at these two. We want to solve for x. Now, if I wanted to solve for x, well, I know those two things add up to 180. So x plus 62 plus 3x plus 90 equals 180. So I don't know what either of those angles are, but I know together they make 180. So let's combine some like terms. 3x plus x is 4x. And 62 plus 90 is 152. We can actually solve for x minus 152 from each side. That's going to give me 28 is equal to 4x. So if I divide by 4, I know x is going to be equal to 7. Okay, let's say our question asked us for more than just x. Let's say it actually wanted the measure of an angle. Well, if I wanted the measure of the small angle, I would plug into x plus 62. I'd say, well, I know x is 7, so 7 plus 62 is going to give me 69 degrees. Say I wanted the measure of the large angle, which was 3x plus 90. If I plug in the 7, 3 times 7 plus 90 is 111 degrees. This one is a special kind of trapezoid. It is an isosceles trapezoid. Now, if you remember isosceles triangles, you remember that their base angles were congruent. Same thing for isosceles trapezoids. For isosceles trapezoids, our base angles are congruent. So in this case, x is equal to 53. So that was probably a little easier than we needed, but it's good enough to illustrate the point. Whenever you have these tick marks, you're dealing with a special kind of triangle, an isosceles triangle. Speaking of isosceles triangles, we actually get some cool things about their diagonals too. Whenever you have an isosceles trapezoid, the diagonals form two isosceles triangles. You also have congruent angle pairs for both the acute and obtuse angles. Let's talk about how we can use that. We want to find the length of JL. Okay, so JL is right here. And we already know it's 8n minus 4, but we don't know what n is. That's okay. We are also given that mk is 12n minus 8. Okay, well, we just talked about on the last slide how diagonals are congruent, and we're given the diagonals on an isosceles triangle. It's told isosceles right here, so we can set those two things equal to each other. 12n minus 8 equals 8n minus 4. Let's go ahead and subtract 8n from each side. And we'll get 4n minus 8 equals -4 plus 8 plus 8. 4n is equal to 4. Oh, this is going to work out nice. Divide by 4 on each side, and n is equal to 1. Okay, I found n. Now I need to find the length of JL. We're already told JL is equal to 8n minus 4. So 8 times 1 minus 4 gives me 4 for the length of JL. This one says solve for all the angles. Okay, so we're going to solve for angles 1, 2, 3, and 4. And what do we know? Well, I see these tick marks, which means I see not right angles. I see isosceles triangles. So if those are this is an isosceles trapezoid. I know this is an isosceles triangle, and this is a smaller isosceles triangle. Let's use that information to solve. All right, if this is an isosceles triangle here at the bottom, then I know that this is also 25 degrees, and I can take 25 and 25 away from 180. In order to solve for my angle measure for angle 1, that's 130. So I know this is 130 degrees, which means I also know this is 130 degrees. Oh, which, if we think about it, means that this isosceles triangle is actually similar to the isosceles triangle below it, because we would have to take that 130 degrees, take it away from 180, get our 50, which would need to be split in between these two angles evenly. The only way to do that is to make them 25 degrees. Now let's look to solve for angle 3. Angle 3, I see a straight line here, and this is a 130-degree angle, so I need to take that away from 180, since all straight lines add up to 180, in order to solve for angle 3. 180 minus 130 is 50 degrees. And then finally, I have angle 4. Well, if I know this is 50 degrees by the vertical angles theorem, I know this is 50 degrees. And then all I have to do is consider that I have this triangle. And I can take that 85 and 50 away from 180. So I have 180. And I'll minus 85 minus 50. That's going to give me 45 degrees. Perfect. Given this isosceles trapezoid, I know it's isosceles because I see these two markers. We want to solve for all the angles. Again, we're solving for 1, 2, 3, 4. Okay, I'll use the fact that this is an isosceles trapezoid, and this is an isosceles trapezoid to do all of this. Now, just like before, I see that I'm going to take this 101, and I'm going to subtract it from 180, and that's going to give me 79, which needs to be split up evenly between these two congruent angles. 79 divided by 2 is 39.5. So I know angle 1 is 39.5. We also talked about how these trapezoids were similar. The isosceles triangles within the isosceles trapezoid were similar. So angle 1 and angle 2 happen to be congruent. So I know that one is 39 as well. Now, in order to solve for angle 3, we need to remember what we remembered on the last problem, in that this is a straight line. So we can take 180, we can minus 101, and we can get that 79 for angle 3. Now, lastly, we have angle 4. If this is a 79-degree angle, if angle 3 is a 79-degree angle, then this is also a 79-degree angle, which means we can use the fact that this is a triangle. And we'll take that 180 and we'll subtract 88 and we'll subtract 79. And that's going to give us 13, which means the measure of angle 4 is 13 degrees. Let's look at this one. Now, again, this is isosceles, right? This is isosceles. So we can say that they're congruent. So x plus 80 equals 8x minus 88. Let's go ahead and minus x from each side. Well, we're minus an x from each side. Let's add 88. Just want to do it all in one step. So that'll cancel, that'll cancel. We have 80 plus 88 is 168 equals 8x minus x is 7x. So we need to divide by 7 on each side. And 168 divided by 7 is 24. 24 is our value of x. That is all for trapezoids.